questions that have come up in the 2D conduction homework. Some people had trouble creating a new material because their view looked like this when they came into engineering data, and this is easily fixed by just dragging that column to the right, and then you can add in the new material and so on. And another thing to keep in mind is when sometimes your views get garbled, you can come to view and say reset workspace or reset window layout, and that sometimes for me has fixed problems with how the things are looking in the windows. For the mesh, we asked you to create a mesh like this with 3 divisions along the x direction and 1 division along the y direction, and you need to have only 1 division here because you have no variation in temperature in this direction. And to do that, you need to put in your sizings on edges rather than on faces, and the way you do that is you highlight mesh and you say mesh control, sizing, and instead of selecting faces, select edges, and let's say I put it on this edge, and I would say scope it to the edges. I would say number of divisions is 1, and I would set the behavior to hard because I don't want ANSYS to change that setting. And then if I say update, I'll get the mesh that I want. In fact, here I want to get rid of that thing that I just added. Let me do an update to the mesh again. Okay, so that didn't change my mesh. There was some confusion about the direction of the heat flow at the right boundary. We ask you for the value of the heat flux over here, and comparing that to the boundary condition that you've given on the heat flux. So first, let's talk about inputting the boundary condition. So you input the heat flux boundary condition. Let me pin this over here, and this is 1 watts per meter squared. Now for boundary conditions, the heat flux by default, as ANSYS assumes, is along the inward normal. Let me explain that by annotating. So this 1 means that it's along the inward normal, and that's the heat flux that you're specifying. Contrast that to when you're probing the heat flux, and let me do that. So I'll solve over here to get the results, and if I go to heat flux probe, so I'm probing the value of the heat flux at that location, and let me expand this, and I'm probing, the orientation is along the global coordinate system. So essentially what I'm doing is I'm probing the heat flux in the global coordinate system. One thing to keep in mind is for heat flux, you always have to keep the direction in mind, or the coordinate system in mind. So when I'm looking at the x value over here, let me annotate that, okay? So this is -3 along x. So since x is in this direction, -3 is going to be in that direction, so the heat flux is like that, and it's 3 watts per meter squared. And compare that to what we gave it, 1 watts per meter squared. So you can see that the natural boundary condition is not satisfied exactly. And as I refine the mesh, I should see this moving towards -1 in this case. So as I refine the mesh, I would expect this to move towards -1. In the homework problem, you have to be careful because it seems like I put in 1 and I get 1 over here, and I would say that, that is right. In fact, let me explain that because that's a little bit confusing. So let's say that my value is 1 watts per meter squared. By the way, I've changed all the inputs so that they don't match the homework. I don't want to give out the answers, but the ideas are the same. Okay, so that's what, if it matched exactly, the value over here would be 1 in that direction. And let's say I get, what I get for the value over here is 1. And the way I need to interpret that is that's along the positive x. So it's going to be in this direction, and that's 1 watts per meter squared. So you